Somewhere beneath a physics lab in Illinois, a particle of light vanished. 30 kilometers away, at the far end of an optical fiber that was busy carrying ordinary internet traffic, its exact quantum identity reappeared. Nothing physical traveled between those 2 points, yet something undeniably arrived. That, in the strictest scientific sense, was teleportation. It has happened thousands of times, in laboratories all over the world. So why don't you have it yet? The strange part, the physics is not the problem. The physics has worked since 1997. What is missing is an ingredient, a material that can catch a fragile quantum state, hold it, and release it on demand without destroying it. For 30 years, nobody has been able to find that material. Now, the search has been handed to artificial intelligence, systems that can imagine millions of crystals no human has ever seen, wired to robotic labs that build and test them around the clock. Serious physicists now attach a number to this. Roughly 15 years to teleportation networks between cities. This is the story of what teleportation really is, what it will never be, and the AI-designed matter that could finally set it loose. First, let's replace the movie in your head with what actually happens. Quantum teleportation was invented on paper in 1993. When 6 theorists led by Charles Bennett worked out a trick that sounded almost illegal. Move the complete quantum state of one particle onto another particle far away, without that state ever crossing the space between them. The recipe needs 3 things. A pair of entangled particles. Particles prepared so their fates stay linked at any distance. A joint measurement, performed on the original particle and one half of that entangled pair. And an ordinary message, 2 simple bits of information, sent by any normal channel, telling the far side which final operation to apply. Do that, and the distant particle becomes the original, the same state, indistinguishable in every way physics allows. There is a catch, and it is not negotiable. The measurement wrecks the original. Quantum mechanics forbids copying an unknown quantum state, the famous no-cloning theorem, so teleportation never duplicates anything. It relocates. In 1997, a team in Innsbruck did it for real with single particles of light, across about 1 meter. The point was never the meter. The point was that the universe allows it at all. What followed was a quiet 2-decade race. In 2004, quantum states were teleported across the Danube River in Vienna, through a cable in the sewer. By 2012, the record was 143 kilometers, a beam fired through open air between 2 Canary Islands, between mountaintop observatories. Then, in 2017, came the result that made the field believe in networks. A satellite called MICHUS caught quantum states teleported up from a ground station in Tibet, more than 1,400 kilometers below it. In 2022, researchers in the Netherlands teleported quantum information between network nodes that were not even directly connected. A real network hop. That same year, the pioneers of entanglement experiments received the Nobel Prize in Physics. And in 2024, that Illinois team squeezed teleportation through a fiber that was simultaneously carrying regular internet data, proving the quantum and classical worlds can share the same cable. Around the same time, Oxford physicists linked 2 small quantum processors and teleported logic operations between them. Photon by photon, record by record, the technology kept answering the same question. Does this scale? Yes. So why is there no teleportation port on the back of your phone? Because light dies. Even in the best optical fiber, photons are absorbed. After about 100 kilometers, most are gone. After a few hundred, effectively, all of them. The classical internet solved this long ago. Every 80 kilometers, an amplifier reads the fading signal and sends out a fresh copy. But a quantum signal cannot be read and copied. That is the no-cloning theorem again. An amplifier is not a helper here. It is an executioner. The theoretical fix has existed for decades, the quantum repeater, a chain of stations that builds entanglement segment by segment, then stitches the segments together using teleportation itself. Elegant on paper. But every repeater station depends on one component physics can describe and nobody can mass produce: a quantum memory. A device that can catch an incoming quantum state, hold it, without measuring it because measuring destroys it, while neighboring stations catch theirs and then release it, perfectly intact, on cue. Imagine catching a soap bubble on a needle, keeping it whole for a minute and handing it to someone else. That is not an engineering problem. That is a materials problem. Try writing the job description for that material. It must trap a quantum state and hold it not for nanoseconds, but for seconds, ideally minutes, while the rest of the network coordinates. It must speak the language of light at telecom wavelengths so it can plug into the millions of kilometers of fiber already buried under our cities. It should work at temperatures engineers can actually field, not only a whisker above absolute zero. And it must behave identically across thousands of stations. Candidates exist, and each one is a brilliant failure. Diamond, laced with nitrogen vacancy defects, holds quantum states beautifully, and is nightmarishly hard to grow at scale. Crystals doped with rare earth ions like europium and erbium have posted storage records measured in hours, but demand deep cryogenic cold. Silicon carbide is factory-friendly, but young. Atomic vapors work in room-sized setups. For 30 years, scientists hunted the way humans always have: intuition, luck, and years of trial and error. The wish list kept reading like a job posting no substance on Earth could fill. The problem was never effort, it was the size of the haystack. Here is the haystack. Take roughly 80 usable elements of the periodic table. Combine them in every ratio, in every crystal arrangement. The space of possible materials explodes into numbers so large they stop meaning anything. Checking them one by one would outlast the universe. Against that, here is what humanity has actually catalogued. After 2 centuries of chemistry, our databases hold only a few 100,000 experimentally confirmed inorganic crystals. That is the haystack we have searched. A thimble. And the pace is brutal. The lithium-ion battery took 2 decades from 1970s lab concept to a product you could buy. And that was considered fast. On average, a new functional material takes 10 to 20 years to travel from discovery to market. Some of our best materials, Teflon, vulcanized rubber, were found partly by accident. If the perfect quantum memory is hiding somewhere in that unexplored space, the odds of a human stumbling onto it by hand are effectively zero. What the search needed was a different kind of searcher, one that never gets bored, never sleeps, and can hold all of chemistry and mind at once. In November 2023, Google DeepMind introduced exactly that. The system was called GNOME, Graph Neural Networks trained on every known crystal structure, then set loose to imagine new ones and predict, from pure computation, which would be stable enough to exist. The output stunned the field. 2.2 million candidate crystals, of which roughly 380,000 were predicted stable. New possible materials delivered in a single paper. Researchers called it 800 years of accumulated knowledge, compressed into months. Let's put the caveats on the table immediately, because honesty is the point here. Predicted is not made. Stability inside a simulation does not guarantee usefulness inside a laboratory. And some chemists pushed back hard, arguing that many entries are close cousins of compounds we already knew. All fair. But step back and look at the shape of the moment. For all of history, the bottleneck of materials science was human imagination. We explored the chemical neighborhoods we already trusted. A neural network has no neighborhoods. It proposes crystals no chemist would think to sketch, because it is not anchored to the intuitions of any single career. The bottleneck of imagination was gone. Prediction alone is cheap talk. Matter has to be made. So walk into a basement at Lawrence Berkeley National Laboratory, where a system called the A-Lab runs an experiment with no humans in the loop. Robotic arms weigh out powders. Automated furnaces fire them. X-ray diffraction reads what actually formed. And when a recipe fails, the AI studies the debris, rewrites the recipe, and tries again. All night, every night. In its first reported run, the A-Lab synthesized 41 brand new compounds in 17 days. Meanwhile, Microsoft's research teams flipped the problem around with a model called MatterGen. Instead of generating candidates and filtering them, you describe the properties you need. This band gap, this magnetic behavior, this symmetry. And the model generates crystal structures to order. Inverse design, materials to spec, like commissioning a suit instead of searching every store on the planet. Put the pieces together and something historic clicks into place. Predict by the million. Synthesize by robot. Test automatically. Feed every failure back into the model overnight. The discovery loop that once consumed an entire scientific career now turns in weeks. And that loop is now being aimed at quantum hardware. Because remember the job posting from earlier, the quantum memory nobody could fill. Piece by piece, machine learning is being pointed at exactly those requirements. Research groups use neural networks to screen thousands of host crystals for rare earth ions, hunting the atomic environments where an erbium ion, which already speaks fiber's wavelength, holds its quantum state longest. AI-driven simulators are designing photonic cavities with shapes no human would draw, that couple light to matter more efficiently than textbook geometries. Machine-learned models of atomic forces let scientists study defects, the diamond-style quantum centers, inside materials that have never been grown, before spending a single day in the lab. And the eternal hunt for better superconductors, the kind that makes single photon detectors and repeater electronics practical, has become one of computational chemistry's favorite battlegrounds. Let's be precise about the claim. Precision separates science from hype. No, an AI has not printed a finished teleportation crystal. The claim is bigger and quieter than that. For the first time in history, the search for that crystal is industrial. It runs at machine speed, around the clock, on 1 million candidates at once. So, where does 15 years actually come from? Not from one excitable optimist. In 2020, the United States Department of Energy published a formal blueprint for a national quantum internet, the kind of document that moves budgets, not headlines. Europe's quantum flagship maintains a staged roadmap of its own. China already operates a 2,000-kilometer quantum-secured backbone between Beijing and Shanghai, using trusted relays for now because true quantum repeaters are not ready. And metropolitan test networks are alive today in the Netherlands, in Boston, in Hefei, teleporting quantum states across single cities. Lay the stages out and the math shows itself. Metro-scale networks, happening now. First field-deployed quantum repeaters, the engineering target for the late 20s. Repeater chains linking neighboring cities, the 30s. Continental quantum networks, around 2040. Count forward from today, and teleportation between cities in roughly 15 years lands squarely inside the published roadmaps. Not a dreamer's guess, but the consensus schedule. Every stage of that schedule, though, leans on the same load-bearing component: quantum memory materials arriving on time. That is the single if holding up the whole timeline, and that if is precisely what AI just started to accelerate. Let's be clear about the prize, because it is not moving bodies. A teleportation network moves quantum states, and that buys civilization 3 upgrades. First, communication that cannot be secretly intercepted. Not because the encryption is clever, but because physics enforces it. Measuring a quantum state disturbs it in a way the endpoints can detect. An eavesdropper betrays herself by the act of existing. For banking, for elections, for medical records, for diplomatic traffic, that is a different world. Second, linked quantum computers. Those Oxford processors teleporting logic between machines were a preview. Connect quantum computers through teleported states and you get clusters more powerful than any single machine could be. The same trick that turned isolated computers into the internet. Quantum power becomes something you access, not something you own. Third, networked quantum sensors. Telescopes on different continents acting as one planet-sized lens. Navigation systems that never need a satellite. Detectors that feel gravity itself shift. Notice what all three have in common. The first teleportation network will not move you a single centimeter. It will move the things your world actually runs on: trust, computation, and secrets. And now the question you have been holding since the first minute. Could this ladder ever reach us? Here is the honest math. A human body is roughly 10 octillion atoms. A 1 followed by 28 zeros. Teleporting you means measuring the quantum state of every one of them, which destroys the original as it reads. That scan's data would dwarf every storage system humanity has built, combined. Physics students at one British university once calculated, half in jest, that transmitting a single human's information at realistic bandwidth would take vastly longer than the age of the universe. But suppose engineering someday crushed every one of those barriers. One question still waits at the far pad. The person who arrives is a perfect reconstruction. Every memory, every habit, every scar. The person who departed is gone, disassembled by the scan. Is that travel? Or is it a copy and a quiet goodbye? Physics takes no position. Philosophers have argued it for decades. Perhaps we never need to settle it. Because the teleportation that will change your life is not that one. It is the one already working. And it needs only a crystal. Now the cold water, because an honest documentary pours it. Objection 1. Prediction inflation. Of those 380,000 computationally stable crystals, only a small fraction have been synthesized by anyone. Some chemists argue that many are minor variations of known compounds. That criticism has real teeth. A database is not a discovery until a furnace agrees. Objection 2. This field has been burned by hype before. In 2023, a material called LK99 went viral as a claimed room temperature superconductor. Within weeks, laboratories and simulation teams around the world took the claim apart. It was not a superconductor at all. But notice what that episode actually demonstrated. The correction machinery of science worked, fast, and computational modeling was part of what made it fast. Objection 3. Timelines slip. Fusion power has been 30 years away for 70 years, and quantum technology has its own missed deadlines. All fair. Here is the difference worth weighing. A quantum internet does not require one miracle breakthrough. It needs steady, compounding materials progress. 1,000 small wins, exactly the grind AI is best at. So far, the milestones keep landing. Measured optimism, not faith. Zoom out one last time, because teleportation is only the most cinematic item on a much bigger conveyor belt. The same discovery engines hunting quantum memories are also hunting battery materials that need no cobalt, alloys that can survive the inside wall of a fusion reactor, catalysts that pull carbon out of the air cheaply, and superconductors that might not need extreme cold. For the entire history of science, discovery moved at the speed of human trial and error. One hypothesis, one experiment, one career at a time. That speed limit is what is quietly dissolving. Call it the industrialization of discovery. Hypotheses generated by the million, experiments run by robots that never sleep, every failure recycled into training data before sunrise. When historians look back at this decade and ask what artificial intelligence truly invented, the answer may not be any single crystal or battery or drug. The invention is speed itself. The compression of the long century that used to separate physically possible from in your hands down into a decade or two. Teleportation simply happens to be the most spectacular thing waiting in that queue. It will not be the last. So run the story back one more time. Teleportation is real. Demonstrated since 1997. Across rivers, between islands, up to orbit, through the same fiber that carries your videos. It moves quantum states. Never matter, never people. Destroying every original as the price of the trip. For 30 years it has stalled on one missing piece, a material that can hold a quantum state long enough to relay it. That search now belongs to systems that imagine millions of crystals in an afternoon, and to robotic labs that test them through the night. That is why sober physicists, the kind who hate headlines, now say 15 years to teleportation networks between cities. Here is the ending worth keeping. The first teleported thing in your life will not shimmer or glow. It will look ordinary. A message no one could intercept. A computation shared across an ocean. A vote that arrived exactly as cast. The future rarely announces itself with a beam of light. It arrives disguised as a Tuesday. If you want to see it coming anyway, subscribe. The next story is already in the lab. Somewhere tonight, a robotic arm lifts a crystal no human ever imagined, checking patiently whether it can catch light. And keep it.